This video will begin our discussion of section 1.4. This is over another approximation method called Euler's method. This one focuses less on graphing and more on an algebraic approach. So what we're going to do, I'm going to show you this picture down here. Please ignore this stuff for now. And we're just going to pay attention to the picture. So the filled-in curve is going to be our actual solution, and how we're going to approximate for this dE is we're going to have a dy dx equals something. We also will have a point x naught, y naught. I can start at this point, and we can pick, and notice right here, these gaps that they have in the x, they're all the same. So they go ahead and they pick, for this method, you'll pick that gap to begin with. So we'll take that gap, and we're going to say, hey, I have a formula that I can predict the slope. So what we'll do is we'll predict our tangent line from that. What that's going to do is we know how far in the x we're going to want to go over, and then we plot our new point on that tangent line. So that's an approximation, that dotted curve, that's what we're doing now in pink, to the solid curve. So I just connect these, and it's a straight line. It's going to be a polynomial check. Now I have this new point, x1, y1. I can put a point there, and I could take that x1, y1, plug it into this formula, get a new slope, and get a tangent line like that. And that would give me my next point. So I would have another straight line. And this is how we would approximate that solid curve here. Now, is it going to be different? Yes, we're going to get gaps and error. As you can think about this in calculus is a common theme. If we make our gap smaller, right? If I were to make this gap right here and then do another vector, I could get closer to the actual curve. So if the step size is smaller, we should get a more accurate answer. So we're not going to use this method to come up with a curve, but what we're going to use for it is to come up with these points that are comparing to the actual point. So there is a formula to this. It's very easy to memorize. It's based on, if we think about, these are a bunch of straight lines, and I want to use the formula for a line that we're probably not most familiar with. It's a point slope form. We actually can, I'm going to throw some zeros in here too for this. We can manipulate this equation around to just get us y. Let's actually not put knots there, but put 2's. There's the second point. All right, we can actually work this out and solve for y2. If I solve for y2, adding y1, then I get this equation here. This equation is what we're going to use. We have different parts of this. This part, m, is dy dx. Right? We just want the line. We want to start with a point. That point's going to be that beginning point. That's where this comes from, x1 and y1. Now you may be wondering, okay, well, this looks different here. What does that mean? That's just the difference in x's. This is what we're going to call h. So our formula is going to be take the y of the point we know, find the derivative, right, at the x and y that we're at, multiply that by h, and add it to y. We're going to get some practice under our belt. So here's some formulas up here, if you're a formula person. This is that form of a line. It's just in different format. It just says that I plus 1 is the next one, right, plus 1. I take the old one, y, and I take the old x and y, and I plug that into, this is the derivative, right? They're just calling it x, dy dx. It says take the old x and y, plug those into the derivative, multiply by whatever the h, remember h is this step size that we were talking about. If you need to find step size, you just take all your x's, take the biggest x minus the smallest x, and divide it by how many partitions you want, how many ends do you want, how many different points do you want to go about. So the whole point of this method is to approximate some function value. It's just saying, hey, I have some function, I have a dE that tells me about this function, but I don't have the function itself, but I would really like an output value for a certain input. So let's take a look at an example. I think it's the best way. This method feels overwhelming at first, but once you wrap your brain around it, it's really just algebra. All right. right, so it says approximate y of 2. We're just going to do A, and then B, we're going to do setup only. All right, so what I do for this, okay, it says approximate some function y when I plug in 2, and they give us this derivative here, dy over dx, and it equals y minus 2x. We are trying to find y. We don't have y. So that's why we're trying to find the approximate for y of 2. Now, this was supposed to have a step. Oh, there's the step size. Okay, so we have our dE. This is going to be our slope, right? And then we have an x naught and a y naught. So I like writing all those down up front. X naught is 0, y naught is 1. They told me the step side is 0.4, so I know I'm going to count up by 0.4s. So x1 is 0.4, x2 is 0.8, I'm adding another 0.4, x3 is 1.2, x4 is 1.6, and x5 is 2.0, and I know to stop because that's what we are approximating. So we want to find all of these y's. I like setting this chart up right here that we just wrote every time at the very beginning. I write down the formula. I would recommend when you're doing these problems to write a formula down every time you start a problem. I also don't assign a whole lot because I understand it's a whole lot on your plate, like problem-wise. So find a way to get this memorized. This may even be something that you put on your note card. So here is the formula. And it really is just slope times the changes of x's added to y. It is point slope form. Okay, so I'm going to identify what that g is. G of xy, that is the derivative y minus 2x. All right, so I need to find y1. So if I'm following this formula, if that's y1, that's right here, that means n was 0. So y of 0 plus h, right, times, and then let's go ahead and put our h in. We already know our h. H is 0.4 times y minus 2x. All right, and this is y naught. So if I want y1, I plug in y naught to 1 plus 0.4 times 1 minus 2 times 0. All right, we end up getting a 1.4. So using this approximation method, we have that if I plug in 0.4, that I'm going to get a 1.4. So now I keep going. I want to know y sub 2. So that is y sub 1 plus 0.4 times y sub 1 minus 2y sub 1. It's always, the right side is always the one before it. That's how I don't mess it up. All right, we're trying to create our new one with the old ones. So I plug those in. I have those on the screen. 1.4 is y1 plus 0.4 times. If I plug in those numbers, we get, let me just grab this from my notes, 0.6, which gets us a 1.64. So you got a 1.64 there. All right, we use the formula again. Y sub 3 equals y sub 2 plus 0.4 times y sub 2 minus 2 x sub 1. That should be an x sub 1. This should be an x sub 2. There we go. So we're plugging all that in now. Y sub 2 is 1.64 plus 0.4 times, and then when I plug x2 and y2 in there, we get 0.04, leaving us with 1.656. That was y3. So as you can imagine, the further we get out away from x being 0 and y being 1 using this, our approximations are going to get worse. The closer we are, the smaller our step size, the better the approximation. So we just keep going of this way. Y sub 4 is y sub 3 plus our step size times the derivative, which is going to be y sub 3 minus 2x sub 3. We plug in all these values. I got 1.656 plus 0.4 times negative 0.744. 1.3584. 1.3584. All right, and then we have one more. We have y to the fifth. Y to the fifth is y to the fourth plus 0.4 times y to the third minus 2x to the fourth. Y to the fourth minus 2x to the fourth. All right, so we just plug in those numbers. 1.3584 plus 0.4 times, if we plug all that in, we get negative 1.8416, leaving us with our final answer of 0.62176. So I'm going to write that here at the bottom. Y sub 2 is approximately 0.62176. So this method is, I find it painful. If I think better, what would work better for something like this is I would probably just build a small program for this. You could probably build one, and my go-to, and you guys are going to laugh, those of you guys that actually program, my only work is in primitive C or in MATLAB. Not a programmer. Anyways, this would be a really cool algorithm if you're into that kind of thing to program, because it would help you understand this method. So it's not great for finding a curve. It's not great for finding the function, but it's great for approximating a value. So let's look at a small application problem, a math application, pretty fluffy applications in math, unlike physics that actually takes account for frictions and air resistance and stuff like that. But here we go. Last example for this. Assume bear population grows according to that differential equation. T being time, maybe y is the population. We have no idea. Okay, assume initial population at t equals 0 is y equals 5. Use Euler's method with step size, h equals 1 to approximate bear population at time t equals 3 years. Before I move on, I do want to mention, I need to go back up here. I didn't set this up. I moved on without it. But what's going to change here, I do want to talk about it, is right here. This is going to go up by 0.1s. It would take us a long time to do this as an example, hence the reason I was just going to talk about the setup. We would want to do a 0, 0.1, 0.2, 0.3, 0.4, 0.5, and all the way up until 2. So we'd actually have quite a bit of numbers that we'd have to plug in. This is when a program would be probably more effective. I'm not going to ask you to do that many on a test. This would be a great type of problem for Euler's method that would show up on a test. Maybe my derivative would be a little more complicated, maybe, but I wouldn't ask you to do a step size of 0.1 just because of how long that takes. All right, let's go back to this bear problem. We have this differential equation. I'm going to write out these t's. So they want to know what is it going to be, what is the population going to be after 3 years. So I'm starting at time equals 0, t equals 1, and they gave us a step size of 1. So that's nice. T1 is 1, T2 is 2, and T3 is 3. We also want the y's. Why not? Y1, Y2, because this is going to tell us the population, or whatever it's telling us in this problem. Y is 5. And then we are going to use the method here. I'm going to write the formula down. Yn plus 1 equals y sub n plus h times g of x sub n y sub n. G being the derivative. All right, so we want y sub 1. That's going to be y sub 0. H is going to be 1. So I'm going to quit writing h this whole time. But the derivative would be plugging in 5 into every y right here. So when you plug all that in, you get a 4.8. So this, just in case you didn't catch on, this is g of xy. So if you plug in x naught and y naught, then we would have 4.8. Let me write this actually with the formula here. It's going to be 1 times g of x naught y naught and then we'll fill this in. Okay, y naught is 5. I can get rid of h, and then now if I plug this in, this is where we should put the 4.8. Now it makes sense. Okay, we get 9.8, whatever that may mean. Now we keep working. Y sub 2 is y sub 1 plus 1 times g of x sub 1, y sub 1. Y sub 1 is 9.8 plus, okay, and we're going to plug 9.8 into every y up there, and we get 27.09504. Adding that to 9.8, we get 36.89504. I like using that big number so I don't make a rounding error. If they ask me to round, I'll round in the end. I don't know if I'm talking about a number of bears, a population density, or anything like that. They just gave that a population grows according to this. Okay, so y sub 3 is going to be a y sub 2 plus 1 times g of x sub 2, y sub 2. So we get 36.89504 plus, okay, and then we plug in that derivative into g. And I did this on my calculator, so I'm going to leave this x2, y2. We just plug it into that big expression up there, and we get 1115.57624. So we get y of 3 is approximately 1,115.57624. I don't want to put bears. I don't know what they're talking about. So could be talking about family units of bears. I don't know. So I leave it at that. So this is Euler's method. Again, it does not help us find curves. It does not help us find solutions. All it does is help us approximate a value plugged into a curve of a DE.